Okay, so as we continue talking about definite integrals, I want to point out a couple properties for these definite integrals, especially now that we've briefly touched upon this area concept with the integral itself. So page 269 and page 270. It's definitely worth your time to flip to those pages and spend a little bit of time looking at table 5.6 on page 269 and then the figures that accompany it on page 270. Most of these things are going to be very intuitive when you look at them and then look at the picture on the next page. So please take a little bit of time and review that. And I really don't think there'll be a whole lot of concerns because the book does such a good job with visually showing you what's going to happen. And if I were you as a student that's being introduced to this the first time, the ones that are probably most important would be figures A, B, C, D, and F. E is a bit of a stretch to start. You can certainly look at it, but feel free to just focus in on A, B, C, D, and F to get the ball rolling on these properties. Okay, so for the next problem, we've got this integral, and we really haven't gotten into too many messy integrals at this point, but even the earlier ones we have, it's always kind of been, if you can't integrate it directly, how can you manipulate the function so that you can simply add one and divide? And not in all cases can you do that. And this is one of those examples where there's really not a lot we can do to just simply add one and divide and come up with something then to evaluate from 0 to 6. So instead we got to think outside the box a little bit. And what we're going to do is we're going to say, take a step back and we're going to say, all right, we know that even though I can't just add one and divide, then evaluate from 0 to 6, I still need to answer the big question. Well, what is the big question? The big question is, what is the area under this curve on this interval? And so as we take a look at this curve, let's go ahead and draw it out and see what actually we're being dealt with. So our function y is going to be equal to the root 6x minus x squared. So what I'll go ahead and do is I'll square both sides here. Y squared equals 6x minus x squared. And now I can go ahead and move everything over to one side to where we'll have this x squared minus 6x plus y squared equals 0. Now some of you might see where we're going with this. It looks like we're going to have to complete the square here with respect to x to get a better feel for what geometric shape we're dealing with. So to complete this square, I'm going to go ahead and put a blank in real quick. And if you're going to complete the square on both sides of the, or on an equation, you got to have a blank on both sides of the equation. So you're adding the same thing. So then half of 6 would be 3, and we square it. So if I put a 9 on the left, I have to put a 9 on the right. Then that left side is going to factor into x minus 3 quantity squared plus y squared. There should be a plus right there, I'm sorry, equals 9. So looks like we have a circle here centered at 3, 0 with a radius of 3. So if I come over now and I graph this, circle at 3, 0. So 1, 2, 3. There's my 3, 0. That's the center. I've got a radius of 3. That's going to put my circle, it looks like, coming right through here and around. So that would be a 6 over there. Now, conveniently, this problem wants us to compute the area under this curve on the interval 0 to 6. Now, to be clear, this is the top half of that circle, right? When we ended up squaring both sides going from there to there, we created an extra part of the graph that we didn't want, right? This bottom part. The range of this is got to be 0 or bigger, so we know that we're the top half of the circle. So that's the area that we want, and that's going to be 1/2 of the circle, which is pi r squared. So 1/2 pi, the r was 3, so we end up with a 9 pi over 2 computation for this integral right here just by using basic geometry. And the big idea is understanding, though, what this is asking. Since we understood what this was asking, we were able to use basic geometry in this one particular problem. Okay, so we'll close out this video talking about the average value function. And the average value function says let f be integrable on the closed interval a to b. If that's the case, then the average value of f is equal to 1 over b minus a, and then the definite integral a to b f of x dx. A couple things here real quick. This average of f, this is a height, all right? This is a y value, if you will. And so I don't necessarily think that viewing the average value function as it's presented here is the easiest way to understand what's happening. So instead, what I'm going to do is I'm going to take this equation and I'm going to multiply this b minus a to the other side. Okay, so when I multiply this over, I'm going to get this definite integral here equals the b minus a times the average of f. Okay, so the single definite integral from a to b f of x dx is going to be this average value of f times the b minus a. Now the reason why I think this is much easier to understand is because when we draw a picture here, let me just draw it down here in this corner of the screen. If this is going to be our function f of x, and this is going to be our a right here, and this will be our b right here. If I mark this off by picking a point, let's just say right here, to where this y value, this is the average of f, okay? When I box that off now, watch what we've just done. So that red box there, for that red box, right, that red rectangle, the b minus a, that's going to be your base. So the base of this rectangle times the height of this rectangle, right, there's the height of it. The base times the height is going to give us the area of that red rectangle. Well, that says that this is now equal to the actual integral from a to b f of x dx, right? That's a pretty interesting statement. By having this set up the way we have, right, and having this average value of f here, the area of the red is going to equal the area now of the blue all the way up here. And it kind of makes sense even in my not so great picture, right? It looks like we're overshooting the area here while we're undershooting it over in this region. So anyway, this is how it's presented most of the time. This is the easiest way I found to understand what it's actually telling us. In doing it, you're just evaluating a definite integral with this 1 over b minus a out in front. So I think you guys can handle that. Now, there's one last thing that I want to mention, kind of closing out this section, and it does relate a little bit to what we've been talking about. You remember, when we talk definite integral from a to b f of x dx, this all goes back to the Riemann sum. And the Riemann sum is us taking all of these rectangles, finding the areas, and then adding them up. An integral essentially takes a bunch of really, really small things and adds them up. Those really small things are going to be the infinitely many areas. The area of the rectangle is going to be your base times your height. We know that this guy right here is your height, right? F of x is always going to be the height. And we know also that that dx is going to be the base. So as you start working these problems, a lot of these problems in the next several sections, I've said it a lot, and it might not have always made sense as to why it was so important, but that dx has to be there. Every time you have an integral symbol, you have to have this differential here. The reason is, without a base times a height, you're not getting an area anymore. So while it does tell us the variable that which we're going to integrate with respect to, the main reason, the big reason that dx or d theta or dt or whatever has to be there is because it's got to give us a true formula for an area of a rectangle, a base times a height. And that integral then is going to sum up all of those small areas that we would have found doing so.